This is the 2-bit adder. Now, this is the final project, and I'm sure you're so eager to see how it works. But first, let me take you through how I built it and how it works. I must run you through the basics of binary addition. To do this, I'll show you a half adder, which is the most basic form of adder. A half adder just adds 2 bits together, represented by A and B. The result of A and B is 1 and 0. Well, this might not look like much to the naked eye, but to a computer, it actually means a lot. 1, 0 actually represents the number 2 in binary, because the sum bit down here actually represents 1, and the carry bit represents 2. And then 2 plus 0 is 2. That's how binary addition works in a nutshell. And this is the half adder. Now, let's move on to a full adder, which is a little more complicated. As you can see, it's a little more complicated than the half. However, there actually is 2 half adders, here and here. There also is the addition of the carry in bit. The carry in bit allows us to do this. If I have bit A and bit B together, I get the carry. Same as usual, same as the last one. However, if I add the carry in, I can have 1 and 1. And since we already learned that this bit represents 2 and this bit represents 1, 2 plus 1 would equal 3. So all 3 bits together would equal 3. That is the full adder. Next, let's move on to the 2-bit adder, which is even more complicated than this. Unlike both adders, we have 4 bits, and a step up from the full adder. However, they work a little differently. These 2 bits represent the number 1, and these 2 represent the number 2, which makes things a little more complicated. Over here as well, we can see that we have 3 output lights, allowing us to display numbers up to 7. However, since we only have the numbers up to 6 to add to, we can't do that. As we can see, this would represent 1, 2, and then 4. And if we look at my example over here, we have 3, so we have 1 and 2, and we have 1, which would represent 4 over here. You just saw the 2-bit adder on the computer screen. However, here it is in person. As you can see, we have our 4 switches, our 3 lights, with it representing 1, 1, and 2, and 2, and then 1, 2, and 4 respectively. It's built on a little breadboard, which allows me to make changes on the fly and make it easier for me. As we can see, if this switch is on, this switch is on, and then this switch is on, that would equal 5 as 2, 2, and 1. And there we go. We have 1 plus 4 will equal 5. But now let's move on to the actual device. As you can see, there's a bit of differences between this thing and the device. For once, the device is built on a PCB, which is a little more tight, more compact, more sleek, more nice looking, just overall better. It's actually the same operation being shown. As you can see, we have 3 and 2, showing 5 down here, as we learned by our place values. Also, the chips are actually not soldered in. They're in chip seats, as you're not supposed to solder chips directly to boards, as that's a big no-no. Power is supplied by the same 9-volt battery. However, instead of it going into this little power jack here on the breadboard, it goes into my little 9mm barrel jack coming up through here, as there is no room for a surface mount. And that's the final design. That's the prototype. Let's go over to multi-bit addition now. This is multi-bit addition. Multi-bit addition works by linking more and more full adders together. As you can see, the half adder in the 2-bit adder links into the full adder. And if we, instead of taking the output of the carry out, if we put that into another full adder, then we'll have another adder. And if we keep repeating this process, we can add more and more numbers. In this example, the number 21 is being made by the numbers 15 and 6 being added together. This is 4-bit addition, as there is 4 adders. Thank you for watching. I really appreciate you taking the time to watch this video.